Hello, everyone. My name is Enhe. So happy to share our research in Black Hat Europe 2021. My talk is Rewrote Your Intent for Privilege Escalation, a universal way to exploit Android pending intents in high-profile and system apps. This is our agenda. And first, I'm gonna introduce the basic concept of intents and pending intents in Android, then give previous research examples, then the key parts of this talk. I'll discuss how to retrieve pending intents and how to hijack insecure pending intents. Then I'll give typical vulnerability cases in real-world app. Most of them are from Android system. And last, I'll introduce our pending intent scanner and great changes about pending intent introduced in upcoming Android 12. Before we start, let me introduce who we are. I'm Enhe in Oppo Ziwu Security Lab. Oppo Ziwu Security Lab was founded by Oppo Security in March 2019. It focuses on security and privacy research in the field of Android, web, browser, and IoT. Wenbo Chen is an independent security researcher. Daoyuan, he works in vulnerability and privacy research lab in the Chinese University of Hong Kong. So, what are intents? Intents are high-level inter-component messages based on binder sent between apps to perform actions. For example, app A can use an intent to perform actions like start activity, send broadcast, start service on app B. An intent has many fields to describe itself, including action, data, component, and so on. If it has component or selector, it is an explicit intent, meaning its destination app is being explicitly set. So if it has only action, it is an implicit intent, meaning only apps declaring intent filter with this action can receive the intent. If it has no field, we call it an empty intent. Then pending intents, the advanced version of normal Android intents, provide powerful inter-component communications on Android. A pending intent holds a base intent that can be executed by another app under the creator app's identity and permissions as if the target app was the creator. For example, app A can send its pending intent with a base intent to app B. Then app B invoke pending intent send to send the base intent on behalf of app A. What if some malicious apps got pending intent sent between? This is a root cause of pending intent security issue. As creators' important identity and permissions, pending intents could be leaked to third-party apps, resulting privilege escalation unexpectedly. The pending intent API include get activity, get activities, get broadcast, get service, get foreground service. Apps use them to generate a pending intent. Note the parameter of the APIs. The intent parameter is right to the base intent. If there is no flag immutable, which is by default, the base intent can be modified later. This flag just began to be widely used to fix the pending intent bug after our research. Also note filling flags, which allow the current selector or component to be overwritten, even if it is already set. Previous research just showed the tips of pending intent security iceberg. There are few cases of hijacking empty base intents. One is in AOSP settings. It's a broadcast anywhere bug. The bug involves complicated interaction between settings, system server, and an authenticator app. A malicious authenticator can get pending intent created by settings at a dangerous action, such as action boot completed, and send it in the name of UID 1000 to send the broadcast to any receivers in the system. This is why this bug is called broadcast anywhere. The other case is in popular app Line, shared in CanSec West 2016. The Line app leaks a pending intent with base empty intent. Then malicious app can get the pending intent created by Line, add a dangerous action and extras, and send it in the name of Line to create a fake push message. So, in previous research, insecure pending intents are retrieved from intent-based intercomponent communications, which actually are very rare. So far, we have the first basic problem of this research. Can we retrieve pending intents which are widely used in slice providers, notifications, MediaBrowser services, and AppWidgets? Only after retrieving them can we exploit further. Let's take a look at the slice provider first. It is a mechanism to share slices between applications. For example, Settings app can share its emphasis setting slice via content-based slice URI to slice viewer app via exported settings slice provider. Then slice viewer can allow user to set NFC in its own user interface. So what are slices? Slices are shareable UIs represented by slice URIs and exposed by slice provider. It contains icon, title, and slice action. And the slice action is implemented with pending intent, as the source code snippet shows. Developers can use Slice View Manager Bind Slice API to bind the slice provider to get a slice, or use low-level content resolver call API, then get pending intent from slice. Here is an example of using content resolver call method to bind a slice provider and get a slice, then get pending intent in the slice. Then let's take a look at notification. Notifications are extremely common in Android system. Just as the picture shows, a notification contains further actions after user taps its content and buttons. These actions are actually pending intents, such as content intent and notification action intent. For example, this source code builds a notification redirecting users to alert detail activity once its content being tapped. So how to retrieve pending intent from notifications? After our research, it turns out apps can implement notification listener service to monitor and listen to notifications, then retrieve pending intent in the callbacks from notifications content intent or notification action intent if permission granted. MediaBrowser service. MediaBrowser service just deals with playing music. MediaBrowser service enable applications to browse media content provided by an application and ask the application to start playing it. A MediaBrowser app can connect a MediaBrowser service and get its pending intent. Sometimes, MediaBrowser service uses pending intent in its root hints. The last one is AppWidgets, which are also commonly used. They are miniature applications, views that can be embedded in other applications, such as the home screen, and receive periodic updates. In short, AppWidget host combined AppWidget in AppWidget provider, get its remote views, and fetch the PendingIntents in remote views. It is through the idle API in AppWidget service implementation. Note the remote views. Remote views is a view hierarchy that can be displayed in another process. It has a commonly used API, set on-click PendingIntent. As the debugging window shows, the PendingIntent is hidden field MPendingIntent in remote views MActions MResponse if it is a set on-click response. It's possible to retrieve the MPendingIntent via reflections. Now, we've fixed the first problem already. Surely, PendingIntents can be retrieved from notifications, slice providers, and AppWidgets. Let's move to the second key problem: how to hijack these insecure PendingIntents, and what do insecure PendingIntents look like. In previous research, we've known PendingIntents with empty base intents are vulnerable. How about this one, PendingIntent with implicit base intents? We've come across so many of these in source code of AOSP and high-profile apps. To answer this question, we have to go deep dive into PendingIntent filling method. It defines how a base intent in PendingIntent can be overwritten. Recalling the introduction of intent, it has many fields. The filling method just treats components and selector as special. By default, they cannot be overwritten or filled in. Other fields except component and selector can be overwritten if not set. With this in mind, we've come up with a universal way to hijack PendingIntents with implicit base intents. So this is how it works. In step 1 and 2, attacker app needs to retrieve an insecure or vulnerable PendingIntent from victim app via methods we discussed before. Then in step 3, he'll mutate the PendingIntent. Since it's implicit, he cannot modify the action field. He cannot modify component or selector either, due to restrictions of PendingIntent filling. But he can register an intent filter with the action, set data or collect data as victim apps providers, set package to his own, and add permission grant related flags. Then in step 4 and 5, the attacker app invokes PendingIntent send to start the activity intent on behalf of victim app. An activity of attacker app will be started. Since intent has grant-related flags and brings victim app's provider URI, the activity has been granted access to provider of victim app at the moment of being started. It can read and write any providers accessible by victim app with grant URI permission equivalent to true. This is the second main contribution of our research on PendingIntent. In short, by hijacking this kind of PendingIntents with implicit base intents, an attacker app can force victim app to grant access of its own protected content providers. So PendingIntents with implicit base intents are vulnerable. We have found many cases on this kind of vulnerable pending intents with implicit base intent in AOSP and some super popular apps. I'll introduce some typical cases of them. The first one is CVE-2020-0188. It's from slice provider, AOSP settings slice provider. It returns a pending intent with an implicit base intent once binded. The POC is very straightforward. Step 1. Retrieve the insecure pending intent by binding the slice provider. Step 2. Modify its base intent and send it on behalf of settings. Step 3. Wait to be opened to read settings provider. The second case is CVE-2020-0389. It is from Notification, AOSP System UI Recording Service. It's from a notification reminding of saving recorded videos. The POC acts as a notification listener service, and first retrieve the pending intent via notification listener service, then modify the base intent and send it on behalf of System UI. Note the clip data. It has been set contact provider, content contact phones. Then wait to be opened to read contact provider, since System UI has read contact permission. As notification is widely used, this kind of vulnerability pattern is very common in many high-profile apps like PayPal, Airbnb, Twitter, Google Drive, Google Play services. We can even get local arbitrary code execution by writing dex jar show to victim app's own providers. The third is an duplicate issue. I just gave an Android ID. It's from MediaBrowser service. There is an insecure pending intent in playback state in AOSP Bluetooth MediaBrowser service. The POC acts as a MediaBrowser, and first, it retrieves the pending intent via MediaBrowser compat connection callback. Then modify the base intent and send it in the name of Bluetooth. Then wait to be opened to read content provider accessible by Bluetooth. The fourth one is in a high-profile app's AppWidgets. It is an insecure pending intent set via set-on-click pending intent. As we discussed before, the POC can act as an AppWidget host to retrieve remote views from AppWidgets, then retrieve the insecure pending intent from remote views via reflections, then modify the base intent and send it on behalf of a high-profile app. Then wait to be opened to read contact provider, since the victim app has read contacts permission. The last one is a very special case. It is in Android System Services, AOSP Activity Manager Service. It returns an insecure pending intent used to control a banned service via Get Running Service Control Panel API. The source code shows two insecure pending intents examples of running services like Notification Manager Service and the Wallpaper Manager Service. Any app can retrieve the pending intents via Get Running Service Control Panel on Notification Manager Service or Wallpaper Manager Service, then modify the base intent and send it on behalf of system server, that is URI 1000, and wait to be opened to read settings providers. There are some restrictions on URI grants from UID 1000. UID 1000 can only grant very few providers permissions in AOSP due to mitigations in URI Grants Manager service, as the code snippet shows. But we found big phone vendors usually allow more providers to be granted or set a special flag to allow granting from system UID. Therefore, this case is marked as moderate in Android AOSP, though it could be dangerous in Android OEM phones. We've come across a few of these examples, but due to time, we're not gonna tell about this in detail. Now I'll introduce how to hunt insecure pending intents automatically. We have designed a suit-based static analysis tool. It will pass APK into Gimple IR, then scan PendingIntent API with data flow analysis to get a result of unsafe code. This picture roughly shows how it works. And first, it will search APIs without immutable. It will analyze and transform Android bytecode to Gimple code with suit. Then locate the statements with the following APIs that create instances of pending intents which do not contain the flag immutable flag, including get service, get foreground, get foreground service, get activity, and get activities. Then search empty or implicit base intents. It will check whether the intent object passed into PendingIntents APIs has invoked one of the following intent methods through the forward flow analysis of a suit. The intent methods include set package, set class name, set component, set class name, and set class. These APIs shows whether the intent is explicit. The forward follow analysis is intra-procedural data flow analysis provided by suit. We have open sourced the tool in GitHub. You can download and try it. By using the tool, we found many pending intent issues in high-profile apps in Google Play. GPSRP even set pending intent bug as known issues, meaning it almost affects every applications. Now, the last section of our talk. What has Google done for these pending intent issues? Google has almost fixed all pending intent issues in AOSP. Also, it has introduced significant security changes in the upcoming Android 12. Most of these bugs are fixed by adding pending intent flag immutable. Some are fixed by using an explicit base intent. In Android 12, developers must specify the mutability of each pending intent for apps targeting above 12. Developers must use either flag immutable or flag mutable. But this kind of vulnerability are still lesser known by Android developers. That's why we decide to disclose this in Black Hat Europe. Also, Google also added a lint rule to detect flag immutable in its official Android Studio IDE. It adds a pending intent mutable flag detector, so developers can check if a pending intent is insecure in its official IDE, very conveniently. There are also some guidelines for developers to use pending intent safely. Developers must create immutable pending intents whenever possible. However, certain use cases require mutable pending intent objects instead, such as direct reply actions in notifications, using instances of car app extender, calling request location updates or similar APIs, scheduling alarms using Alarm Manager. These pending intents require flag mutable. So in these cases, it's strongly recommended to use an explicit intent and fill in the component name. But it is still vulnerable in some cases. Sometimes, to use a mutable pending intent with explicit intent is still vulnerable. This is a real-world example. A pending intent in notification aiming to be start hidden main activity, which can process an intent extra. Since the pending intent has no flag immutable and its explicit base intent doesn't set the extra, a notification listener app can still hijack the pending intent and fill in the extra, resulting in another classic intent redirection vulnerability. So I have a final advice for both developers and security researchers. Every pending intent without flag immutable needs to be carefully reviewed. This is a final advice. This is my talk about pending intent security. Thank you for attending.